Hello everyone, this is Professor Keen. We have been talking about Chapter 3 in A Student's Guide to the Great Physics texts, where Simplicio, Segredo, and Salviati are discussing falling objects and the relationship between the speed of a falling object and, first of all, the weight of the object, and secondly, the density of the surrounding medium. They've been critiquing, particularly Salviati has been critiquing Aristotle's theory of falling objects. So in my last lecture, we talked a bit about that. What I'd like to do in this lecture is speak for a couple of minutes about some of the discussion that Galileo makes about neutrally buoyant objects. That's not the term that he uses. It's a term we use nowadays, neutrally buoyant objects. It basically means that they do not rise or sink when placed in water. So at this point in the dialogue, Galileo discusses an interesting experiment he carried out in order to make a ball of wax neutrally buoyant. So how to make a ball of wax neutrally buoyant. This is a bit of a diversion, although it's related to what we've been talking about. Okay, so how do we do that? The idea is that if you have a ball of wax and you put it in water, so imagine that's the ball of wax, you put it in water. Here's a cup, and we'll say you fill it with water like this, and this is your wax right here. Because wax has a lower specific gravity or lower density than water, the wax will tend to rise. But Galileo says one thing that you can do in order to make it stay neutrally buoyant, that is, wherever you put it in the water it stays there, is to press tiny grains of sand into the ball of wax. So although wax has a smaller specific gravity than water, sand, which is rocks, limestone or something, has a larger specific gravity than water. So if you were to just take a little rock, for example, this is a sand grain, it would fall in the water because it's more dense than water. Wax, on the other hand, would rise in water. So if you take these little grains of sand and you sit there and you press them into the wax and then put the wax in the water, if you do it just right, you put just the right amount of sand grains into it, you can make overall this wax ball, together with the sand embedded in it, the same density as water, and hence you can make it neutrally buoyant. So how do we figure out how many grains of sand we need to put into this ball of wax? So how many sand grains must be inserted? This is one of the homework problems that you have, and I just want to lead you along in the direction that you would take in order to solve this problem. This is an interesting problem. So the goal, essentially, is to make the density or the specific gravity of the ball to be exactly equal to the density of water. That's, if you can do this, if you can make the overall density of this the same as that of water, that would imply that this is neutrally buoyant. Well, what is the density of water? Let's use the CGS system of units. This is not the system of units that Galileo uses, which kind of makes sense. The International System of Units wasn't invented until the 1800s, or right around the turn of the 18th century, 17th, I guess the 17th century turning into the, what did I say? The 18th century turning into the 19th century. Napoleon. So Napoleon was oversaw the implementation of the International System of Units. Anyhow, we want to use that, and in the International System of Units, specifically using centimeters, grams, and seconds, the density of water is 1 gram per cc. So we want the density of the ball to be exactly equal to 1. Of course, the density of wax is less than 1, the density of sand is more, but the composite we want to be equal to 1. What is the density? Well, the density of an object is the mass of the object divided by the volume of the object. So here we want the mass divided by the volume to be equal to 1. Well, what is the mass of this ball? The mass of the ball is going to be equal to the mass of whatever wax we have there plus n times the mass of one sand grain, where n is the number of sand grains. So, for instance, if we have one sand grain, we would just add on to the mass of the wax the mass of one sand grain. If there were 2 sand grains, you take 2 masses of a sand grain, 3 and so on. So n is the number of sand grains. And if you're listening up here, what we're trying to do is we're basically trying to solve for this n. That's eventually what we're going to try to figure out. Okay, so this expression here is going to go up there with the mass of the ball. What about the volume of the ball? What is the volume of this ball? Well, it's going to be the volume of the wax, whatever that was, plus n times the volume of one sand grain. So we take the volume of whatever wax we had to start out with and add on the number of sand grains times the volume of each individual sand grain. And once we do that, we'll plug that in here. Okay, so how do we do that? Let's go ahead and plug these mathematical expressions in. A lot of solving these physics problems, by the way, is converting your thoughts that are in English or some other language into mathematical equations and then solving those equations. And that's somewhat of an art form, okay? So let's plug these in. The mass of the wax plus n times the mass of, I'll just write 1 sand grain, divided by, here's the volume of the ball, the volume of the wax plus n times the volume of 1 sand grain, and we want that to be equal to 1 gram per cubic centimeter, gram per cc. So I guess I should put that over here too, 1 gram per cc. And again, what we're trying to solve for is this value n. Okay, well, what is the mass of the ball of wax? Well, the mass of the ball of wax is going to be equal to the density of the wax times the volume of your ball of wax. And what's the volume of the ball of wax? That is going to be, well, if it's a ball, I guess we could use the equation of a sphere. The equation of a sphere would be 4/3 pi times the radius of the wax ball cubed. You may or may not remember that formula. 4/3 pi r cubed is the volume of a sphere. Okay, and what else do we need to put in here? So that's going to go in up here. The volume of the wax is going to go in there. The mass of 1 sand grain, we need to know what that is. The mass of 1 sand grain would be the density of sand, and I guess we'd have to look up whatever the density of the rocks that sand is made out of, maybe limestone or something, times the volume of 1 sand grain. And what is the volume of 1 sand grain? Well, let's just assume, for the sake of argument, that it is also a sphere, 4/3 pi times the radius of 1 sand grain cubed. Okay, so we could, if we were, for example, given the radius of the sand grains and the type of sand, we would have the density of the sand, the radius, we could figure out the volume, we could plug all that stuff up in here, then we would basically have the volume of the sand grain, the mass of the sand grain. If we're given the radius of the wax ball, we could find the volume of the wax and the mass of the wax, and we would have some equation that depends on the radius of the wax, the radius of the sand, the density of the wax, and the density of the sand, and we could plug all those numbers in and solve for n, right? So we could do that. That would involve some algebra, rearranging this formula, but we basically want to solve this equation for n. And remember, n was equal to the number of sand grains required for neutral buoyancy. And that is how you approach a problem like this. And this is the problem that Galileo mentions in his text, and I think it's kind of an interesting question. This, by the way, is something that fish do all the time, not add sand grains to wax, but basically in order for a fish to float without rising or sinking in the water, it needs to make its density equal to that of the density of the ambient water. And the way it does that is by means of bringing in air or expelling air through its mouth, for example, into its swim bladder. So it basically needs to make its overall density match that of the ambient water. So this is something that biological organisms, specifically fish, do all the time. Okay, so I think I'll stop there, and then we'll come back and pick up Galileo's discussion of falling objects next time.